Okay, guys, welcome back. So the question here, we said the data is going to be added to the system. And in our scenario that we have in the desk, remember what we have. We have, let's say, bucket 1 or the bucket p minus 1, 0 up to p minus 1. Then in this case, if we have done space, I need to use overflow. This is my way in order to work or cope with organizing or growth of the data. But we are going to do what? We're going to take a look at a different way, okay? To find another way, more smart way in order to handle the overflow, or let's say the growth of the data actually. We try to stay, remember we said, to try to find the way and have the optimal access of the data or optimal performance to use the hash table at most to this kind of auto operation. One, to locate the bucket, the second access, or let's say access the data in order to fetch the actual data from the disk. That I'm planning to do. Try to reduce the overflow. How can you do that? We do actually two more, different, hashing technique we can use. Okay, this is what we call the first one. It's called extendable hashing, and the second one, the linear hashing. Today I'm gonna hopefully finish the extendable hashing. And I'm gonna give you an example so you can expect what kind of question you're gonna expect in the exam. So the midterm, by the way, is gonna be up to the extendable hashing because I'm gonna give you more time in order to prepare for the exam. Okay? Anyway. So what I'm going to do here, let's go over the way that we review the way that we handle the group of the growth, then we see why it's a bad idea, what I can do here. So when many keys going to be inserted in the hash table, then we have used overflow. Overflow, that's going to ruin, the overall performance, okay? Because it requires for me to increase the number of disks and out operation in order to receive the data. And let's give you the worst case scenario. Every time you're looking for the item that's stored in the end of the overflow blocks, the last overflow blocks associated with each bucket. So we can do what here? We can reduce the number of blocks. How can I do that? The simple thing I can do what? I can increase the size of bucket, right? So if we take a look here, let me give it a second. So here, assume that we have 0 up to p. Let's say the number of buckets from 0 up to 9. So the hash function that I use what? X module 10, all right? For example, the simple hash function. So this bucket, then after that we have overflow here. Right? So the way that I can handle overflows, what I'm going to reduce the overflow, what I can do, how about increasing or expanding the number of buckets that we have? Up to 20, for example. Let's say up to 19. So instead we have 10 buckets, p equal 10. I'm going to increase this one to be up to 20. So in order to increase this one, what you need to do here, if you change the hash table size, this one requires what is called rehashing. Rehashing all the keys in the hash table into the new hash table size. So in this case, if you have this one, the old one, if you increase the size of whatever the bucket that you have, that means definitely you're going to use different hash function. Right? So what I need to do, I'm going to add or take all this input again and rehash them into the new bucket from 0 to 19. The data is going to be different. And it makes sense. For example, let's say at the beginning here, when I say 10 modules, 10 is going to give me what here? 0. But using this one, 10 module 20 is going to be hashed to 1, to the 10. So here, instead the item that we here, it's going to be now hashing to the new bucket here. You see that? So again, the way that we handle the overflow, reduce the number of overflows that we have, that we're going to come up with change the hash file or the hash table size, the number of buckets there. If we change this one, that's me require for me to do what? Rehashing all the keys. This is expensive operation, right? So can we do better? Yes. The best way to do that, we're going to do what's it called, talk about the dynamic hash table. The dynamic hash table, that means in this case, instead to rehashing all the keys, okay, that's in the hash table, I can do what? Only fraction of the existing search key needs to be rehashing, not all of them. So like a magic way, instead to hashing the entire data, maybe I'm going to say, okay, maybe only this one is going to be rehashing to the new bucket. So it's going to be perfect to the performance. Yeah, that's what we're planning to do using the dynamic hashing. Clear, guys? So let's see how can we achieve that. So remember, we can achieve this one using two different ways: extendable hashing or linear hashing. So what's extendable hashing here? We talk about extendable hashing here. So what's extendable hashing here? It's going to eliminate what? The need of use overflow. So one way to do that, remember, we try to do what? Only fraction of the existing search key needs to be rehashing, not all of them. Plus, extendable hashing give me an extra, one plus, one advantage. Okay? That said, there is no overflow in this technique. So you can build hash index. This is key, but okay? This is the way, how can we handle the collision? Regardless whatever hash function we're going to use, yeah? Remember we said the hash function and the way that how can we handle the collision, yeah? So that's the way here. Building extendable hashing or hashing technique, and in this way, there is no overflow. But every time when you're keeping adding data, you feel that all the blocks or buckets are going to be overflow full, you need to do what? You have to double the size. That's bad. We prefer the linear. Linear is much better. Okay? So for the extendable here, for example, I assume that you have only 10 buckets. Yeah? So if all of them full, or you need space, one bucket is full, what you need to do, there is no overflow. You cannot use overflow for the extendable. So in this case, you have to double the size. This you have the simple example. If you have 2 buckets, if you need more space, so this one 2, you're going to end up, you have 4. If you need more, always double the size. You're going to end up, you have 8. So it looks like 2 to the power I, and the value of I is going to be 0, 1, 2, 3, 4, and etc. But at least you don't need to rehash all the value, and at the same time, there is no overflow. Linear hashing, the size of the hash table, this advantage here, it's going to be increased linear. For example, I give you 1 bucket, it's not enough. Okay, I give you another one, 2. Not enough. I give you another bucket, 3. So at a time, 1 bucket at a time. So this means I'm not going to waste the space. But the problem, we cannot eliminate 100% that chance that sometimes you're going to have an overflow. What we're going to see is not the way that similar to number of overflow blocks that are going to be added, similar to the one that I showed you at the beginning of today's lecture. So it's going to be much better. We're going to see that the linear hashing is much better than the extendable hashing. How can you build the extendable hashing? Then we have an example how it works, how to perform insertion. Just the one that you're going to perform here. By the way, here the data is shrinking and expanding in the way that it's going to be exponential, which is going to be double in the size, 2 to the power something. Okay? So extendable hashing. Here, I'm going to split the bucket instead letting the chain of the growth forever. So in this case, remember that what we did in the B+3, if you have a node is full, what you need to do, you have to split this one. So if you have 1 bucket, I can split this bucket into 2 buckets. Instead, you have overflow. So this one is going to have 1 bucket and another bucket. Then you need to do what? Rehashing the data that's stored in this bucket, the old one, that end up will have overflow between the 2 buckets, because you're going to split this one. The same thing that we did at B+3. A node is going to be overflow. Okay, what I have to do, split, create another block or node, then rehashing the data or redistribute the keys. Of course, in the B+3, because the data can be evenly distributed, or the data is sorted, so it's easy to distribute them. Here is different. We're going to see how can we perform that. Okay, here the way that I handle is going to depend on the hash value that I have. Okay, so the bucket array can grow by doubling in the size. Okay, so when you talk about the bucket array, it's going to be doubling in the size. So it looks like you have different structure a little bit. Actually, this is the structure that we have here in general. If you take a look here. I'm going to use different name. The array is the memory with the hash value to the disk. We call this one directory. This another name. And those here we're going to call the bucket array. It's already the bucket array. This is the block state. So we do have a directory and we have what we call the bucket array. Let me draw this one here. It's better here. So generally speaking, you have what? The extendable hashing is the dynamic hash technique. We do have a directories and the buckets are used to hash data. Remember the mapping from the hash value to the whatever the bucket that you're looking for. We call this one a directory. For example, I assume that we have only 2 entries in this directory. Okay? So here we're going to use what's called the global parameter. Let's go one step before that. When you compute the hash value is going to produce a number of bits. Assume the number of bits is n. I'm not going to use all of them. I'm going to use only the I bits, one bit at a time. Either it's going to start with the left or the right. In this class, we're going to start only on the left. So I consider only the first I bits here from the hash value. Assume the hash value is going to produce, for example, 4 bits. So every time you compute the hash value, you're going to say 4 bits 1 0 1 1. You have 0 0 0 up to 1 1 1 1. Okay, all the possible values. When you compute the hash value, I consider only the first bit or the first column. Take the first bit here. Since we have two directives 0 and 1, I'm gonna say the value of I equal 1. That means how many bits that you're gonna use from the hash value in order to determine or decide how many number of entry you have in the direction. If the I equal 1, that means in this case 2 to the power 1 equal 2. So I have two entries in the direction, 0 or 1. Clear? This is the most important thing. You need to know what the hash value, and each hash value is gonna have number of bits, has a specific value. I'm gonna use only the ith bit in order to tell me what the bucket index that you have, or how many entry in the directory that you have. These directives point to the bucket, so we call this one the bucket array. Okay. So I will use the ith bit to tell me how many entries here. And these ith bits also at the same time tell you which bucket, when you say how many entries, at the same time tell me which bucket I need to follow to store my data. So if the value is whatever the hash value that's computed, let's assume 1, whatever, I don't care about the rest. I care only about the first bit of I is 1. I follow 1, that means the value here, and they say, okay, the data is going to be stored in this bucket. Okay? And so the value of I, or the global parameter, has two things. Tell me how many entries in the directory here, and at the same time tell me which bucket I need to store my data. Okay? We do have another parameter here. We call this one the value of j, or the local parameter. The local parameter is going to tell me here how many bits you want to use in order to determine the membership of the entry within this block from the left. Either use 1 bit or 2 bits or 3 bits. Let's give you another example here. Assume we have this situation. For example, the value of I equal 2 bits. So they have 2 to the power 2 equal 4. Then we have 4 entry. How can we organize them? It's better to use the binary representation because I'm going to use the number of bits, 2 bits from the left. So the binary representation is going to be easy. 0, 0, 0, 1, 1, 0, 1, 1. Or 0, 1, 2, 3. Okay? So the value of I is going to say equal 2. Assume the hash value of x equal whatever value. I'm just consider the ith bit, the first I bits, in order to determine where, how many buckets we have, and also where. Find the pointer to the bucket there to store the data. Sometimes you're going to see that we have a multiple slot in the directory that we have here. So now we have 4 slots, okay, can point to the same bucket. Sometimes you have this. Why? Because here at the beginning, remember, try to reduce the number of buckets that I'm going to use. Okay? And at the beginning, we're going to note some of them because the data that's going to be stored, it's small. It's not too much. So can fit in one or few buckets. So that means at the beginning, we're going to see I will show you, by the way, how to build this one for the beginning and the end. It's going to be much clearer. But keep in your mind here, we do have a multiple slot can be what? In the directory, can point to the same bucket. Why? Because the data is small enough and in order to reduce the space. Okay? So in this case, since we have a multiple slots in the directory or location in the directory can point to the same bucket. So the data can be mixed. Yeah? Because remember, I'm going to use the first 2 bits here in order to determine the membership. Here I need to have another parameter in order to determine the data that can be stored here. Has specific conditions or must be agree on the first j bits. So I'm going to use the local parameter, for example, 1. So this means all the elements, for example, that's stored here, the first bit from the left must have the same value. Otherwise, you cannot store them here. So you see here, for example, if you have the data, let me give you an example. You can see 0, 0, 0, 0, 0, 1, 1, 1, 0, 1, 0, 1. All of them start with 0, 0, 0, 1, yeah? So all of them fit here. And here, since I can use only 1 bit in order to determine the membership, if there is a space. If there is no space, then I need to split. So generally speaking, the local parameter, always the value of j less than or equal the value of outer parameter. Is it clear, the structure a little bit here? So if you understand this one, then the rest is going to be easy. Okay? So we said 2 integers. Use the global parameter, which will be the number used in the hash key to look up for the hash bucket, and also control the number of slots in the directory here that we have. And we have another thing we call the bucket label, or the local parameter j, with the number of bits of the hash value, all of the hash value, okay, that's used in order to determine the membership within this bucket. That summarizes what to talk about here. Okay, good. Here, when you say the j equal 2, so specify all of them must have agree on the first 2 bits. Okay. Okay. Now the most important thing here. This is the first very important slide. If you try to insert a new entry to the index, what we need to do, this is very important, okay? The slide 41, 42, and 43, they are going to use them and do the insertion, okay? Well, we do have examples, don't you? We have many examples to go over this one with more details. So the first one, in order to insert the record, insertion, deletion, whatever, you need to do what? You need to compute the hash value. Then the hash value is going to do what? Tell you where the bucket that you're going to help you to store your data. Okay? But here we're going to do what? I'm not going to use the entire hash value. I'm going to use the first I bits. By the way, you can use the last one, but here in this class, please, all of us use the first I bits. Okay? From the left. So you compute the hash value, then go to the bucket index by the first I bits of the hash value that you're going to compute. Then follow the pointer, because here it's going to tell me for the hash value, see the hash of x or k, this one will give you the hash value. I need to compute the I bits. The I bits can tell me which entry or slot in the directory. I follow this one to find the bucket. Then I'm going to see, do you have a space? Yes. If you have space, I'm going to insert the search key. We are going to only insert the search key, okay? Of course, you have to insert the search key in the pointer. But for simplicity, we're going to use the search key. Here, we are not going to store the search key. We're going to store the hash value. Why? Because it's easy for us to help us in order to work later. But actually, you have to insert the search key and the value with the pointer where the record is going to be stored. Okay? Let's store that. If there is a space, insert, then done. If there is no space, so that means this bucket is full. For example, this bucket has 3 entries, and I already have 3 entries. Now when you try to insert the new one, it will be here. So what I have to do here? Generally speaking, we need to split. Always. But remember, we need to make sure that when I split this one, I will create a new bucket. I need to make sure that I do have enough pointer in the bucket area, or in what is called, the directory, in order to point to this one. Let's give you the simple scenario here. Assume the value is 0, 1, the I is equal 1, okay? Then here, this one, point here and point here, and here, for example, j equal 2, or equal 1, sorry, and the value here, we have value and we have value exists here. And the hash value of k is equal, let's say, 1, 0, 1, 1. Okay? So what we're going to do here, I will take the hash value, take the first I bit, in order to determine, using the directory, tell me where the directory, which bucket I need to follow. So it said 1. So you have to go here. 1, they said, please follow this pointer. Here we have 2 entries. The what I'm going to do here, I'm going to say 1, 0, 1, 1. Okay? There is no space. What I need to do, this one must be split into 2. So in this case, this one is going to be deleted. Then we have 1, and we have 2 blocks, right? The problem, if I split this one directly without testing the value of I and j. In other words, if the value of I and j are equal, then we do have a problem here. Because if you split, create a new block, so you didn't have enough pointer in the directory here in order to point to the new block. And this makes sense. You see, you have only 1 pointer. So I'm going to use this pointer to this. How about this? There's not enough pointer. So you need to check the value of I and j. If the value of I equal the value of j, this means you need to do what? You don't have enough pointers in the directory. This means you need to double the size. You need to add more buckets. That's the meaning here. Clear? If the value of I is not, let's say you have the second scenario with the easy one. The same one here, we have I equal 1, and we have, for example, 2 pointers here, 2 buckets, and j equal, let's say I equal 2, because as we say I equal 1 does make sense. For example, we have many buckets, okay, 0, 0, 0, 1, 1, 0, 1, 1, and we have the value of j equal 2, something like this. Okay, the hash of k is equal, let's say, this is the pointer 0, 1, 0, 1, 1, 1. So you take the value of I equal to 0, 1, follow here, follow this pointer. This we do have like oh, this I try to yeah, it's okay. Value j equal 1, yeah. I want to give you the situation that we can split without any problem. See this one. Sorry, you hit me. Something like this. So in this case, what we're going to do, this one is here full. When you try to insert one item, this is going to be inserted here. It's going to be 4. So in this case, this one's deleted, and you create a new total blocks. Okay, redistribute the keys among the two buckets. Then, since the value of j is less than the value of I, that means here you do have enough pointer in the bucket. In the directory, you can use them in order to point to the old bucket and the new one. So I can use this one here and use this one here. So again, just try to explain to you here. If you try to insert an item and there is a space, then done. If it's going to be overflow, we don't have overflow. What we're going to do here, it depends on the value of j and I. If the value of j less than the value of I, that means you can split safely. Split, create a new block, that means, or bucket. Then after that, you need to redistribute the keys with only in this portion. A fraction of the bucket is going to be, or the key is going to be redistributed. And also you need to adjust the pointer. Yeah? If the value of I equals the value of j, you cannot split. Here, actually, in both cases, I need to split. But here, I cannot split easily or safely. Because this is a split, you're going to add a new block, and this block is going to be standalone. There is like a dangle block. There is no pointer associated with this one. So in this case, what I need to do here, I need to expand add extra bucket or entry or slots in the directory. So the value of I is going to be increased by 1. Then after that, now we can split and do this one easily, because now we're going to be turned to the first scenario, first case. Both cases you need to split, but one of them you have to double the size of the bucket first, then after that you can split. Make sense to you guys? Good. If the value of j of the local parameter is less than the global parameter, so that means you can split safely, then you can redistribute the keys. How can you do this one? So I have one block. Assume this is in the j. Okay? The value j equal 1 and the value of I equal 2, for example. Okay? Good. So in this case, I need to do what here? I'm gonna split this one. When you split this one, what does that mean here? You create another bucket. Okay? Then, when you create another bucket, how can you distribute the keys among these buckets? You're gonna distribute based on the value of j plus 1. So that means 1 bit is not enough, or the count value of the j value from the left, it's not enough. I need to add 1 extra bit in order to determine the membership between both of them. Because if you use the same bit, the value of j bits, you're gonna still, all of them is gonna be the same place. But I need to redistribute them based on the value of j plus 1. That means add 1, consider another extra bit from the left in order to determine the membership between them. So you're gonna distribute them here. Then after that, you just adjust the pointer to the new one based on the value of j plus 1. Then you need to update the value of j to be j plus 1. So again, split the block into 2 blocks, distribute the records based on between the old and the new one based on the value of j plus 1 first bit. Yeah. Then after that, update the header of each block to the j plus 1. So here, j, for example, equal 1. I'm going to say j equal 2, j equal 2, because I consider 2 bits now in order to decide the membership here within this one, which makes sense. Then adjust the pointer to the hash, to the bucket. Okay? Then done. If sometimes even j plus 1, we're going to see later this one bad thing here. For example, if all 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, something like this, okay? And 0, 0, 0, 0. For example, the j, assume that we have only 3 spaces here, can allow to store 3 tuples, or 3 entry. The j equal 1. When I insert another new item, the first value for j, it's not enough. I mean, so that means I need to create another 2 blocks, and you want to redistribute the keys among these 2 blocks. In this case, when you try to use the j plus 1, all the 0, 0, 0, 0, 0, 0, 0, 0, all of them are going to be in the same bucket. So I need to do what? Continue doing this one. Split and create another j plus 2, based on the value j plus 2. So in this case, 3 bits. Oh, 3 bits now, finally. I managed to have, for example, this and this is going to be one block, and this is going to be another block. Okay? So the most important thing I want from you, these steps here. And I'm going to repeat them in the example and also in the, let's say, the exercise that we're going to solve to help, answer together. If the value of j equal to I, or j equal to I want to split, but I can't. I need to do one extra step. What I need to do here, that means the current value of I is not enough, so increase I equal I plus 1. Add 1 bit. That means instead of using the first I bits, I'm going to consider the first I plus 1 bits. Add 1 extra bit from the hash value. When you add this one, then double the length of the hash bucket or the directory. Remember, assume that I, for example, equal 1. So I have 2 to the power 1 equal 2. So we do have 2 buckets here, 0, 1, in the directory. If you consider 2 more, extra bits of the value of I equal 2, so that means that this one is going to be expanded to what? In order to have like 4, right? Because we have 2 to the power 2 equal 4 integer slots here. How can you do this one? How can you expand that? So it looks like what we're going to do here. When you expand this one, it looks like this one is going to be expanded 2 parts and to the half. So this one is going to be 0, 0, 0, 1, and this one is going to be 1, 0, 1, 1 with the new value. Right? So in other words, if we have a bucket, the entry here, the value of the current value is W, whatever, regardless whatever the value of that. And this one used to point to the block B. Okay? So this one, when you expand or double the size, for every single entry, you have to double the size. What does that mean, double the size? That means the W now is going to have W0 and W1. 2, divided into 2. Both of them is going to point to what? To the B. Because I double only the entry in at the, what you call the direction. Clear? So that's why if you have a 0, it's going to be 0, 0, 0, 1, and the 1 is going to be 1, 0, and 1, 1. I adjust 0, 1 in the right. That means the double. And you continue this one. So this one, if you wanted to double this one, oh, this is a problem. It's going to be larger. 0, 0, it's going to be here. This one is going to be 0, 0, and 0, 0, 1. And 0, 1 to be 0, and 0, 1, 0, and etc. So you have 8 entries. And remember, all of them, those are going to be pointing to the same block that's used by 0, 0. And this one is going to be pointing to the older block that point by 0, 1. Okay? Then once you double the size, now the value of j is, or the value of I is going to be greater than the value of j. Then you have to go to the step, the previous step, that means do this. Let me summarize what we're going to do. You try to insert a new item, okay, in your search key. You compute the hash value. And it depends on the first I bits of the hash value. The value of I is going to be equal to 1, the 1 bit, then after that 2, 3, 4, and etc. Okay? The first bit, or the I bit, it determines to you where's the block you need to store your data. Go there. If there is room, perfect. Store the data, then done. If not, or not, it depends on the value of the parameter of the, you have 2 different scenarios. Whether the local parameter of this block, and by the way, which block I need to consider? The one caused the problem. The local value is less than, say, the global parameter. Yes, that means a split, redistribute based on the value of j plus 1, the keys. Then after that, update the local value or the parameter for the old and new block. Then after that, adjust the pointer from the directory or the hash table. If the value of j equals the value of I, the local equals the global, that means you cannot do this step yet. You have to expand the directory size or slots or the bucket that we have. Then after that, you have to do, you can do the first step. You can do the split. Okay? Okay. Let's have examples. The first one to take a look. I give you the hash, for example. Of course, we're going to talk about, give you some assumption. For example, the bucket can store only 2 entries, 3 entries, 5 entries. So in this case, the bucket is store 2 keys, okay, can be stored here. And we store the hash value just for simplicity, okay? They're going to be stored here, okay? So I will say, for example, give you some assumption about the hash function. I'm going to say the hash function is going to produce this hash value. I'm not going to bother you to compute the hash function, so I'm going to say, okay, you need to insert these values. I give you the hash value. So for example, you see that the I equal 1, the global parameter here, we have 2 slots in the directory here, and we have 2 buckets, and this pointer each of them. If you take a look, the j equal 1, that means the first bit must be for every single one must match, and here j equal 1, that means the first bit from the left must match. Clear? I said insert this key. I'm giving you this is the complicated scenario first. When you try to insert the key, the value of I equal 1, that means you consider only the first bit, 1. 1, so like hash the value, it will be 1 0 1 0, check 1, that means follow this pointer. The data is going to be stored here, so it's going to be 1 0 1 0. Alright? I will store this one here. Is this enough space? No. Overflow. What I need to do? I need to check the 2 scenarios. Actually, you need to split them. Create another bucket, then you distribute the keys. But if you do this one, you can have a problem. What's the problem? If you split them, another bucket, so where's the pointer of this bucket, the new one? Do you have enough pointers here? No, we don't have enough pointers. So we cannot do this one. What's the reason why? Because the value of j is equal to the value of I. The local parameter equal this one. So we cannot do this one. The only thing you need to do first, you have to expand this one, or double the size. So instead you have 2 entries, you must end up, you have 4. Why? Because I'm going to say the value of I equal 2 plus 1 to the power 2 is going to be 4. So this one is going to be expanded. How can I expand this? To show you here. This one is going to be expanded. So 0 is going to be what? 0 0 and 0 1. So we have 1 2. Correct? Right? The one is going to be what? 1 0 1 1. You add just 0 at the beginning. Then the 0, this one can point to this one. So this one, both of them is going to be point here. Yeah, and this one, both of them is going to be point here. I expand the size. So the value of I equal 2. Do we have any problem here until this moment or until this step? I would assume no. Okay, good. So what's the next now? So now the value of j is less than the value of I. So can you split safely? Yes. Remember, this one have 1 0 1 0 here. Then what I have to do here? I will split this one into 2 blocks. I create another block here. Okay, then I'm going to redistribute the keys from this one, not here, this one that's caused a problem with the new one, based on the value of j plus 1. So based on those 2 values. So first 2, 1 0 1 0 1 is going to be in the same place, 1 0 0 1 1 0 1 0. I don't care about the order within this one. Yeah, and the other, actually, I made a mistake here. So redistribute this one among 2 keys. So this one is going to be moved here. And this one is going to be 1 0 0 1 and 1 0 1 0, and increase the value for j equal 2 and the value of j equal 2. Then you need to adjust the pointer based on the value for j. So that means the value is j 1 0 2 bits. So the 1 0 is going to be point here. I use different color. And this one, since we have 1 1, so the 1 1 is going to be point here. You see now we managed. That's what we're going to do here. Clear? Let's do the next. So that's what happened here. Then after that, I need to expand this one. Then after that, I need to create or split this one after expanded. Then I need to split it. Then after that, to redistribute based on the value for j equal 2 plus 1, I mean. Then you need to adjust the pointer. And then end up we have, this is just the way that just try to insert this item. Okay? That's how can you insert 1 0 1 0. So assume that we have this. And I said, now that's what we have right now. So insert this and this. I give you 2 keys of the hash value. I will give you the hash value directly for simplest. So 0 1 1 0. In order to hash this one, let's do the steps. I will consider 2 values, the first 2 bits from the left from the hash value, which in this case 0 1. 0 1 follow the pointer. 0 1 here, it's here, so 0 1 1 1. What do you need to do? You need to do anything else? No, because we do have space, so this is perfect. And you check here, the value of j equal to 1. Okay, so the first bit must match. And also you can check your solution. How can you reach this one? In reach this one, you have to compute the hash value, then you consider the first 2 bits, and you are in the right place. Clear? So we're done from this one. And this is the result that you have. Now I need to insert the 0, 0, 0, 0, the hash value. Consider basing the value of I here, 2 bits from the left. 0, 0, 4 here, the value is going to be 0, 0, 0, 0. We do have a problem. What? It's overflow. But what's the value of I and j? The value of j is less than the value of I. That means you can split and you have enough parameters or enough pointers at the directory you can use in order to point to the new bucket or new block. So in this case, what I'm going to do here, I create a new one here. Okay, and redistribute the keys based on the value of j plus 1. So I need to consider the first 2 bits from the left. So the first one is going to be 0, 0, 0, 1, 0, 0, 0, 0, and this one is going to be moved here. Then adjust the pointer. When you adjust the pointer, this one is going to be no more here, and this one is going to be here. And to check based on the value for j, of course I need to increase the value for j by 1, and based on the value for j, you can use which pointer you're going to use from the directory to point to this bucket. 0, 1 must be 0, 1. Clear? Okay, so that's what happened here. Then I increase this one, and we end up, we have this. Okay? And this edge. Good. How about insert 1, 0, 0, 1? I think in the worst case scenario, give you maybe up to, you're going to expand this one, double this one up to 2 to the power, I think 3. In the worst case scenario, okay? I think 2 to the power 3, I guess, or 2 to the power 4 if I hate you, if I'm mad at you, okay? So let's do this one. Insert 1, 0, 0, 1. You see the procedure is easy, just you need to practice. 1, 0, 0, 1. 2 bits, 1, 0, 1, 0, follow this one. I'm going to sort this one here. Can you split this one? Yes, but the problem if you split to create another one, they don't have enough pointers to point to this one. Yeah, you see that? We don't have enough pointers to point this one. So what I have to do in this case? The simple thing we're going to do here, since the value of j equal the value of I need to double the size of the bucket. So that means the I is going to be equal what? 3. So it looks like for each of them here, it's going to be 3. This is just for simplicity, okay? 0, 0, 0, 0, 0, 0. You see, 0, 0, 0, 0, 0, 1. And this one is going to be 0, 1, 0, and 0, 1, 1. And this one is going to be 1, 0, 0, and 1, 1, 1. And this one is going to be 1, 1, 0, and 1, 1, 1. And the pointer, each of them is going to be pointing to the same place. Right? Which that's what we did here. Just expand this one. 0, 0 would be 0, 0, 0, and 0, 1, 0. 0, 1 is going to be 0, 1, 0, 0, 1, 1. And both of them still point to the same place. This is just, I doubled the size. You see, that's what we did. Now, the value of j is less than the value of I. What you need to do? Split. Create another one here. Then redistribute the keys. And just speaking, by the way, split this one in the bottom, okay? Because in order to have the organized, make sure that I don't want from people do something like this. This pointer here, the pointer here. Please make it organized. So anyway, I create a new one. Then after that, adjust the pointers here. Based on the value of j plus 1. So based on the first 3 bits here. 1, 0, 0 together, and 1, 0, 1 is going to be here. Then after that, you need to adjust the pointers, and this is the all. Okay? And the exam either give you like a structure like this in the beginning, and said, for example, this give you something like this. I'm gonna say maybe perform some series of insertion. I'm not gonna ask you about the deletion, by the way. Just to give you, I want from you to insert. Okay? The deletion is gonna be a reverse operation. That means you need to merge them. Merge, then you reduce the number of, instead we have a j plus 1, we get a j minus 1. And instead we use, for example, if we double the size, you need to shrink by double. But we are not going to cover this one. Only I want from you to know the insertion. Give you structure, I mean, either going to be given extendable hash table with the following entry, then I want from you to perform this set of operation. Or something similar to what I will share it with you, by the way, this file. This is just an example, okay? Something like this, okay? I will upload the solution after the class. It's already there. Then let's do this one together. So first of all, what I ask you here to do, by the way, you can increase the say, I think, zoom in new browser if you cannot see that. Thanks to Adam. Notify us with that. Anyway, so that's what I have, okay? So how can I perform this operation? You see, I will give you some information. I said the bucket can hold two pointer pairs. That means you have 2 keys can be stored here. Maybe you're gonna say 3, maybe you're gonna 4. So I have only 3 entry or 4 entry. Then I give you, actually it's not 6, it's 7, okay? It's 7 objects, okay? With the following key are inserted to the index in the following order. You have to do this order one at a time. Then you assume that, for example, you're going to use extendable hash table. Sometimes you're going to use the linear because both of them have different ways. For now, we just study the extendable. The linear we're going to study next week, but the exam is going to be up to this moment, up to this part. Okay? So, how can you, since they said extendable hash table, since I want to start doing this one from the scratch, I'm going to show you the initial index state or index table. The initial, some textbook, they said the I equal to 0. I'm not a big fan of this one. I'm going to start, this looks like insert the data, and you are not going to consider any bits. Does make sense. So anyway, the initial value, the value of I equal to 1, and this is the way that I'm building here. I'm going to say I equal 1, okay? Then here the value of 0 and 1. Then both of them is going to point out to what? To the bucket. This is the initial value. Let's do this one the way that we did in the class. J equal to 0, and this one has nothing, empty. This is the initial index table when it's empty. Index table, okay? Now starting with it. They said insert the first one, 1 0 1 0 0. I want to insert the first one. Take the first bit, 1 bit, 1, and it's going to be inserted here, yeah? So in this case, 0 1, I equal 1, and this one is going to be inserted here, J equals 0. Let's have a different color. I'm going to insert this one, it's going to be the value, the first one. It will be 1 0 1 0 0. Okay? We're done from the first one. The first one, you can, by the way, do 2 in 1 because here I have 2 slots, so I can do 2 insertion. You can combine them, it's fine. Then the second one, you need to insert 0 0 1 1 0. The first bit 0, follow this one. You do have a space 0 0 1 1 0. I don't care about the order within this one. Okay? Within the bucket. So far, so good. Now let's try to insert, let's say 1 1 0 1 0. In order to insert that, the first one I is gonna be go here. 1 it's gonna be inserted. All of them point to the same bucket. So you have something like this here. 1 0 1 1 0 1 0. It's overflow. The value of J is less than the value of I. What you need to do? Create another block, another tuple, yeah, or another bucket, and this one you need to redistribute the keys based on the value of J plus 1. So based on what? 2 bits. Okay. So in this case, the J equal to 1. So 1 bit 1 here, and the bit of 0 is gonna be here. So this one is gonna be empty, and this one is gonna be 1 0 1 0 0, and the other one will be 1 1 0 1 0. Clear? Let me do this one. So this is the third one. Clear? Let's do the other one. So after that, I need to insert this, say 1 0 0 1 1. Of course, by the way, you need to update the value of J equal 1 and the value of J equal 1. Clear? I'm gonna just click here. That means I'm gonna erase everything. Then let's do the situation, what we have right now. So we reach this point, we have the I equal 1. That's what we have here, 0, 1. And we have a pointer here, feasible to, let's say, j equal 1. And the value is going to be 0, 0, 1, 1, 0. And the value for j equal 1, another bracket. And the value 1, 0, 1, 0, 0. And the other 1, 1, 1, 0, 1, 0. And the other point. That's what we have so far. Okay? So now we need to insert 1, 0, 0, 1. 1, 1. Which is this one. The value of I equal 1, 1 bit, follow here, we don't have space. So what I need to insert this one is going to be overflow. Right? So what so can create a new bucket? No, I can't, because the value of I equal the value of j. That means you need to what? I need to double the value of I for all the buckets that we have. So I'm going to say I equal 2. So that's means 2 to the power 2 equal 4. The value is going to be something like this. In the directory 0, 0, 0, 1, 1, 0, 1, 1. 0, 0 is going to be pointed to this place. 0, 0, 1, 1, 0. The value of j equal 1. And here, this one, and actually both of them pointing here. And 1, 0 and 1, 1 is going to be point to the one that caused the issue here. J equal 1. And we have 1, 0, 1, 0, 0, 1, 1, 0, 1, 0. And we have 1 here as overflow. Then now we have a space, the value of j less than the value of I. What you need to do here, I need to create another bucket, and this distribute the key based on the value of j equal 2. So 2 bits must be. And here you can tell 1, 0 together, and 1, 1 is going to be together on the other side. Okay? So in this case, it's going to end up, we have what here? 1, 0, this one, 1, 1, 0, 1, 0 is going to be here, and here it's going to be substituted by 1, 0, 1, 0, 0. Okay? And you can tell j equal 2, and the first 2 bits must match. And here, you need to adjust the pointer. So now the 1, 0 is going to be here, 1, 0, and the 1, 1 based on the value of j, 1, 1 is going to be point here. So we're on the right track. Okay? Then you're going to continue to do the next one. So now we have this. Let me write what the result that we have. Then after that, we try to insert another one, which is going to be make sense here. By the way, the previous one, you can insert 0, 1, 0, 1, 0 because you do have space. Yeah? So anyway, after insert 1, 0, 0, 1, 1, and 0, 1, 0, 1, 0, that's what the situation that we have. 0, 0, 0, 1, 1, 0, 1, 1. Okay, the data here. So I equal 2, and the j equal 1 here. You see that the different value of j, each bucket has its own value. Okay, 0, 1, 0, 1, 1, 0, and 0, 1, 0, 1, 0. This one, both of them here, point is here, and this one point here, and this one point here. Okay, 0, 2, 1, 0, 0, 1, 1 is stored here, and the second one, 1, 0, 1, 0, 0, and the third one, or the third bucket here, that we have a j equal 2. Then in this case, we have 1, 1, 0, 1, 0. Okay, that's the scenario that we have until now, the situation. So now I want to insert 1, 0, 1, 1, 0. How can you insert that? That's the problem here, because if you insert 1, 0, let's have a different color. 1, 0 is going to be where? 1, 0 follow this pointer here, and here it's going to be 1, 0, 1, 1, 0. There is no space. Can it split? No, because the value of j equal 2, the value of I equal 2. That means you cannot split easily. So what we're going to do here first, you cannot split until you double the size. When you double the size, now the value of j is going to be more complicated. Okay, let me just share with you the solution. So I will, give me a second, just I will give you the solution. So the solution is going to be exists there. It takes time just to convert the file. Yeah, it's here. You see, so this is already, the initial case that we have. Then now starting the items one at a time. As you mentioned, you can't combine 2 or 3 steps if you have a space. In the exam, you have to give me something similar to this one, okay? Or the way that we use, but you have to show me your steps. Don't jump and say, this is the final answer. No, it's not gonna accept it. You have to show me how to reach this. So anyway, when you try to insert now 10110, I try to insert 10110, and this one can be inserted here, yeah? Let's do this one here. Overflow. So what we're going to do, we need to expand this one. So this one is going to be, for each of them, the first one is going to be 000001. And this one is going to point to what? To j equal to 1. Yeah, 0010. Just I want to show you this. 110 and 01010. Okay? Then this is the first one. The second one too is going to have a different color too. I will just I delete that. Anyway, so that's what happened. You see that all of them, this one used to be what here? Used to be 00 and 01. 00 is expanded 2 parts, and 01 is going to be expanded 2 parts, but both of them is going, all of them is going to point to the same location. Expand, double. Remember we said W is going to be point to what? W0, W1, and both of them is going to be point to the same block that used to point by the double. So if you have, instead you have one arrow, one pointer, we do have 2 pointers for each block you're gonna add, or bucket you're gonna add. Then once you perform this operation, you're gonna set and you have the data and continue insertion. I think, yeah, I mean, sometimes you're required to have maybe up to I equal 4, but I'm not sure whether they give you an example in the exam or not, because I don't want from you to do, I mean, spend a long time to answer this question. So this, I mean, what they call the extendable hashing. Remember, what you're doing, search, look, perform the hash function, go to the actual bucket. If there's a space, store, then done. If not, take a look at the value for j and I. If they are this, the value for local parameter less than the global parameter, so now you can safely split, create a new bucket, redistribute the keys based on the value for j plus 1, update the local parameter with the value for j plus 1, then adjust the pointer from the bucket to, or from the directory to the new pointers. Okay? If the value of j equals value of I, you cannot do this step yet. Do first double this, the entry or the bucket in the directory. Then after that, now you can end up, you have the situation that the value of j is less than the value of I, so you can repeat the same operation. Okay? Okay? So what do we mean? Why we need to have another hashing techniques? Why we cannot using whatever the extendable hashing? Because we saw that last time, it works fine, yeah? Allow me to do what? Dynamically do what? We don't have overflow, yeah? And we do what in this case? We manage to reflect to any change of the data, yeah? When you increase the size of the bucket, or double the size of the bucket, we don't need to rehash every single component or every single block. Only we have like a fraction of the blocks of the data is going to be rehashing to the new position. So what's the problem with this one? Why we cannot use it? Actually, from the name, for the main disadvantage of extendable hashing is what? The size of the bucket array would double each time the parameter I increased by 1. Do you think that's a good idea? It's not good idea. I'll give you like a scenario that we don't like. Use extendable hashing in order to answer this, or in order to use it as a building block in order to create hashing table. Okay? Anyway, assume that you have this situation. For example, you have like one bucket. In one bucket, we do have 2 tuples or 2 entries, and all of them are going to have what? They have, for example, 20 zeros, and then after that we have 1, and 20 zeros, and we have 1, maybe 1, 1. Here we have 19 zeros, and we have 20 zeros. The size of the hash value is 21 bits. Okay. Assume that the value j equal 1, and the I is equal, let's say 2. We have 0 and 1 can be hashing to the same place. Okay, then now we need to insert another entry, and this entry is going to have 19 zeros, and say the final one is going to be 1 0. Okay, so this one must be hashing in this place, because the base of the value of I, the first letter is going to be 0, or the first entry. Yeah, so it can be hashing here. The problem with this one, you need to remember when we hashing, check the value of I with the j. Yeah, if the value of I less than the value of j, then you can split safely. What's going to happen here? I think it can be second. I think I'm going to use the whiteboard in order to make sure that I have enough space. So this is the scenario. So I equal 1 or 2, for example, or whatever the value of I is 0, 0, whatever the value of I, this is equal to 1. Okay, and we have the j equal to 1 here, and we have 0, 0. We have 20 zeros, and this have 19 zeros, and you have 1 1, and now we need to insert another number which have 19 zeros, and you have 1 0. This one must be entered here. Yeah, since the value of I equals value j, they need to double. So we'll double this one, then you have a 0 0 0 1 1 0 1 1. Okay, the 0 0, all of them is going to be pointing to the same place. All of them point to this one. Now the value of I and the value of j equal 2, and the value of j equal to 1, and the value of I equal 2, so I can safely split and redistribute the keys. When you split, you figure out that all the data is going to be where here. So all the data must be in the same block. So we still have, for example, let's say A, B, C. A, B, C must be in the same block. So when you split, when you try to distribute the keys among the two buckets, you figure out that the data is going to stay in the same bucket. So here it looks like doing this one, maybe you require for her to have to the power I bucket in order to find a way finally and being able in order to store this data, let's say, in two different buckets. So we figure out that we keep double the bucket array or the directory that we have. This is going to be like an expensive operation, going to waste the space. We're going to have a large bucket array or let's say directory here, whereas I'm trying to store a small amount of data. So there's a waste of the space, and at the same time, this is not practical solution. Did you understand the problem here? So we don't like this one. So how about if we manage to come up with another hashing algorithm? We call this one linear, okay? Which looks like exhibit what's called the near optimal performance, both in terms of access cost and the storage load. If we have to find another or better solution in this case. So instead we have like every time if we have a space or we need to say increase the directory or the bucket array by, I'm not gonna double the size. I'm gonna say, it looks like this algorithm. Now we have, for example, 2 buckets. Do you need more? I'm gonna give you only 1. Do you need more? I should give you another 1. So it's not double of the size, it's gonna go linear, okay? Of course, the cost that in order to achieve this goal, may be required to have like kind of some of overflow. So in this case, we try to figure out a better way in order to build the hash algorithm in a way that every time you need a bucket to add, I'm not gonna double the size of the directory. I'm just add 1 bucket at a time as needed. Okay? That's what we call the linear. So let's go over this one to see the details behind this one and why we need to use it. Okay? So the linear hash table has like a different story. Is it dynamic? That means it's gonna grow and shrink automatically as needed. Okay, but the grow is gonna be by linear. That means 1 at a time. So in this case, it has 2 parts. Okay, the first one you compute the hash value. The hash value is gonna produce what? The hash function will produce the hash value. The hash value in this case, for example, has p bits. The same thing. I'm gonna use 1 bit at a time if we need. It looks like I bits. I'm gonna use the low order bits of the I. So I'm gonna use the smallest value here, not the highest value. Only the lower value. With the value of I that's used in order to help me in order to, let's say, find the hash value and find the exact bucket where I'm going to store the data. It's different a little bit, but just to have different strategy, okay? So let's do this one first, okay? I can use this value, hash value. I know that I'm gonna use the low order bits of hash. And the file is gonna go linear. This means it's not double. Every time I'm gonna add 1 bucket at a time. So it's gonna save the space. That's what I'm looking for, okay? So let's have some parameters here. The main parameters that we have here, I'm gonna divide the data of the bucket that I have into 2 parts. The one that's available, the one that's not available. It's gonna be clear later, okay? And you have the growth rate, as we mentioned, is gonna be linear. And also, when you need to decide that you need a space. For example, in the previous algorithm, what's called the extendable hashing, we decide that we need to double the size or increase the bucket size, or to say the array or the directory that we have that contains the bucket array by double when? If the value of I is equal to the value of j, and we do have like overflow, right? Here, it have a different strategy here. The decision I'm gonna perform in order to tell when I need to add 1 extra, let's say, bucket. This means you have to follow what is called, the following criteria. The average occupancy per bucket, the average occupancy that we have, must be greater than, for example, some threshold, okay? Then that means we need to have to split the bucket into two. In this case, that means we need to add one extra bucket. Okay, so in order to decide when we're going to increase the size of the bucket, it looks like we have specific criteria that can be generalized as the average occupancy per bucket can be greater than some threshold. And we can specify what's the threshold. Keep this one in your mind later when you take a look to the more, the property and the attributes, or let's say the component of the hash, or let's say linear hashing. We're going to see that how can we decide this one, what exactly that the criteria means, and how can we achieve this one. So it looks like not the based on the value of I and j. We don't have I and j. Here's a different story. Here we don't have like basic specific criteria and basically specific, let's say, threshold. Which is threshold gonna be given? Okay, let's say the average occupancy per bucket in general is gonna be 85%, for example. That's the threshold that we form. If we exceed this one, that means I have to split. Or add another split, that means I have to perform what is called, the add extra, let's say, bucket. Okay? We do have an overflow. If you compare this one using what is called the extendable hashing, we don't have an overflow. Here, the price that we have to pay in order to have a linear, increase the size of the bucket, that means must have what's called the overflow, because I have to wait until this condition is satisfied. And the criteria that violation, for example, find the number of occupancy, or let's say, generally speaking, the average occupancy is going to be greater than the threshold. That means in this case, I have to split. If not, that means maybe there's a chance, there's a time that we're going to do what? We have like a bucket is going to be overflow. That means I'm going to use an overflow block. Okay, but don't worry, we're going to see that based on computation later, maybe after the few operations, you're going to do what? We're going to get rid of this overflow if every time you're adding, let's say, one extra layer. Okay, we're going to use the low order of the bits of the hash value in order to help me in order to decide on mapping which are the key into specific bucket. I need to go over some parameters, usually there. Then these parameters are going to come to handy later in order to help us. How can we define? How can you say specify the requirement? How can we use this index in order to hashing the data? Just speaking, we do have like a parameter n here. The value of n, let's tell you that right now it's denotes or represents what? The number of buckets that actually used. Maybe it's weird a little bit. Let me give you a simple example. The value of I, by the way, has a different meaning here, okay? Of course, it's going to be the number of bits that we're going to use in the hash value, okay? But it's going to help, can be derived basically the value of n. Let's do this example. Assume the value of I equal to 1. Or let's say I equal to, say, 2. That means in this case we have 2 to the power 2 possible number of buckets you can have. So the total is going to have 4 buckets. This is 0, 1, 2, 3. Okay? Actually, we are not going to use all of them. So we're going to use one at a time. So maybe you're going to have, for example, I use 2 buckets. So the value of n is equal to 2, which is going to tell me what is the number of buckets that actually are currently in use. It's not the number of buckets available. What I currently am using. I use only 2 buckets. If you need another more, for example, you're going to use more, for example, you need to add bucket, you see that you have total 4 buckets, you can use them in total, based if the value of I equal 2, based on this equation. But we are not going to use them. We're going to use one at a time. If you need space, I'm going to give you another one. So in this case, assume that, I compute the average occupancy, that the criteria that we're going to use in order to decide we need to add, or to say split. When you say split this piece, you need to add, let's say, a new bucket. Okay? So assume that to achieve this criteria, with the goal, the condition is true, this means I need to add. That means in this case, I'm going to add, say, n equal what? I'm going to add 3. So the value of n is equal 3. That means the total number of buckets that in currently use, 3 out of 4. You still have another one. If you need, you can, use it later. If you need this one again, then you can use this one to this value of n equal 4. If you need another one, now we're going to say, I need another one. But I don't have available buckets here based on the value of I. Then in this case, the value of I equals 3 because I need to add another bit. That means we have 2 to the power 3. That means the total number of buckets available 8, but we're going to use, for example, only 5 of them. If every time you need one, you're going to add one. Is it clear? Does that make sense? What do you mean the number of buckets that are currently in use? the value of I can be derived from this equation, log 2 to the of n. That means, in other words, we define the value of I different a little bit here, the number of bits that we need to use in order to represent the bucket index in the binary representation. For example, let's give you an example. If n equal to 1, so how many bits you need to define or represent the bucket index in this case? Remember, the bucket index is going to be how the pointer tell you, for example, how can we index every single bucket in the directory here. The first one, this means 0, the second one is 1, the third one is 2, and etc. Okay? So that means if we have number of current buckets used is n, that means I need only one bit in order to represent that. So I can say the first bucket, that means it's going to be bucket 0. Okay? If you have 2 buckets in use right now, so that means it looks like here, we have 2. This means you need to have the same one bit, either 0 or 1. 0 is going to be this bucket 1, and 1 is going to be bucket 2, because you start from 0 up to n minus 1, something like this. Okay? Or up to p minus 1. Remember, when you use the hash value, actually we're going to use the same hash value, x modules 2 to the power I here, in this case. That's what we're going to use. I'm going to talk about this one later. If the bucket is, let's say, n is equal 3, so that means you have 0, 1, 2. In order to represent 0, 1, 2, the first bucket, the second bucket, the third bucket, I need to do what? 1 bit is not enough. So I need to have 2 bits. So in this case, it's going to be 0, 0, 0, 1, 1, 0. Okay? If you have 4 buckets in use, that means you still 2 bits are available, enough in order to represent every single, or indexing the bucket that we're going to use here. Is it clear? So that means if n equal 5 up to n equals, say, 8, that means I need to have what? 3 bits in order to represent the numbers from bucket 0 up to bucket 8, which up to n minus 1. Okay? So when you talk about the buckets in general here, if we have n buckets here, so this means the number is going to be from 0 up to n minus 1. And here you need to specify, depends on the value of n, how many bits you need to represent all of them from 0 up to n minus 1, which is going to be the value of I. Which is, in other words, how many bits you're going to use from the, because if we have from 0 up to n minus 1, we're going to use I bits in order to represent all these indexing. That means I need just to consider the first I bits, or the low order of the hash value, in order to tell me where I need to hash this, whatever the search key to which bucket. Okay? Okay, this is the one. There's one important, to say, property here. We have value of n and the value of n minus 1. It's going to come to handy later, okay? So if the value of n equal n, 2 for example, we notice that if you have value of n, every time if you take a look to the binary representation of n minus 1, we'll find out that the first bit of the n minus 1 always have the value of 1. Always. Which is going to be the suffix. Always going to be equal to 1. What does that mean here? Assume the value of n equal to. How many bits you need to represent this one? Only 1 bit. Yeah? Okay. In binary, take a look to the n minus 1, which is going to be 1. What's the 1 in binary? Is 1. The first bit is going to be in the left, or the suffix is going to be always equal to 1. If the value of n equal 2, how many bits you need to represent this one? With the value of I equal 2. It's going to be, if the value of n is equal 3. So that means you have 0, 1, 2, because always you have from 0 up to n minus 1. This is the number of buckets that, or the index of the bucket that you need to find index to it. You need to find how many bits in order to represent them. 0, 0, 1, 1, 2. That means 0, 1, 2. That means I need to have 2 bits in order to represent that. If you take a look to the n minus 1, if n equal 3, which 2, binary representation is going to be 1, 0, and the first bit, or the suffix here in this case, is going to always equal to 1. That's a very important property. It's going to help us in order later when you try to sign. Remember we said maybe you're going to have to the power I bucket available, but here right now I'm using only n buckets. So what if the hash value is going to be greater than n? Where it's going to be hashing? It's going to be hashing to non-existent bucket. Or let's say bucket is not in use right now. It's not available. So what I have to do here? We are going to map this one to one existing there. Or one bucket is that, or into, let's say, existing bucket. I will talk about this one. This is the motivation why you need to take a look at this one. Anyway, back to the slide. So you notice that if the value you're given the value of n, okay, if you take a look to the binary representation, n minus 1 always going to find out the first bit from the left, or let's say the suffix of this binary representation always equal to 1. So we can generalize this one. The value of x, if the value of x is greater than n minus 1, and the value of x less than 2 to the power I minus 1, remember if we have, for example, I equal 3, that means 2 to the power 3 equal 8, that means we have from 0 up to 7, right? These are all available buckets that we have, from 0 up to the power I minus 1. So that means if they're given any value of x, which the x is going to be n minus 1, or the value that any hash value, it's going to be greater than n minus 1 and less than 2 to the power I minus 1. Always, the first bit always equal to 1 for the binary representation of this number. Do you agree or not? Yes, because if n minus 1 is the first bit 1, any number greater than this number, it's going to be also going to have 1. So that means it's going to help us a lot later. Hold this thought for a while, then let's take a look to the structure, how it looks like. This is a simple example. So here there's the parameter that we have. I'm going to say the value of n equal 2. That means I'm going to use 2 buckets. 1, 2. Because we have 2 indexes. Okay? Or you can say this is the directory and this is the bucket array. In general, since index 0 and 1, I need n equal 2. How many bits for the I need only 1 bit in order to represent that. Good. So this one and R is going to be the number of records that you have. How many to enter? You have 1, 2, 3. So the value of R equal to 3. Okay? If you take a look at the content here, we are going to take a look only to the last I bits, all the bits from the right, in order to check whether the input is going to be belongs to this one or not. This is equal 0, index 0. So this one, the first value must be equal to 0 here. So we never that we have 1, 0, 0, 0. This never exists. And this one equal to 1, that means all the tuple or integer going to be inserted here must equal to 1. We're going to see this one later. But right now, this just give you an example, how it works. Okay? By the way, the number, we can have different names. Maybe you can use the logical and the physical one. That's another way in order to represent that. Okay? So this is the logical. We can call this one the logical, let's say, hash bucket. And this is the physical hash bucket. That means this is actual blocks that's stored in the disk, and this is the logical. Okay, you have 2 to the power I possible one. Now we use both of them. Okay, so take a look. If I hash a value here, you have a search key, compute the hash function. The hash function is going to produce a fixed number of bits. We just want to focus in the first I bits, or the last I bits if you go to the right. I'm just to focus on the last I bits. The I bits is going to be here based on the value in order to make it easier for us to find out the right index that we need to hash. Of course, this one it looks like you have like an indirection. We have the value of hash value and tell you which index you need to follow. Okay? So anyway, so you compute the hash value. It's going to be 1010. Later, we're going to see that we're going to take this one into, let's say, decimal format. So it's easy just to figure out the value that I want or index that I need to log into. Because here we're going to notice that we're going to use from 0 up to the power I minus 1, which is the total number of, let's say, buckets that available. Okay? Let's do one thing here. Here I can divide my buckets into 2 parts. Since we said the value of n is going to be what? Which is, the number of buckets that currently in use. So it looks like here, we do have the total number of buckets here depends the value of I, 2 to the power I. From 0 up to 2 to the power I. I'm not going to use all of them at a time. If you want a time you want to do, I'm going to use only n. And the value n is going to be increased by 1 as needed. So here we can divide this one into 2 parts. From 0 up to value of n, since we're going to use n, let's write this one. Those are the n buckets in use. So from 0 up to n minus 1, okay, we call this one the real bucket. What does that mean? The bucket that actually used. That's the meaning here. We do have some extra bucket we are not going to use right now. They are there available as needed, but we are not going to use because we don't need them. We call which the value that's greater than anything greater than n, up to the power I minus 1. Which in this case we call this one the virtual bucket. So we see that, for example, sometimes let's say assume that we can say the value of n, for example, equal to 1 or 2, or let's say I have a specific number here. Let me give you an example here. I think I can give you an example, it can be much clearer here. Okay, assume that we have this situation. So we do have, for example, n equal 3, okay? And n equal 3, how many bits is the value of I? That means I is much equal to 2. I need 2 bits in order to represent that. So this is the structure, how it looks like. I'm gonna have what's called the logical hash bucket. I will call this one logical because easier to work with. And we do have like the physical, the one that has the actual bucket that's gonna be stored in the disk. So it looks like we have a level or indirection. This one, the logical, just show you how can we index or find out which hash, let's say, bucket that I need. For example, the first bucket, go follow this pointer. The second bucket, this is gonna be follow that pointer. Okay, so this is the physical. Let's say hash bucket. Okay, and this is the information going to be, this is the first bucket. Assume that we're going to use the n equal 3, for example. That means 0, 0, 0, 1, 1, 0. Those are the used one. We agree with this one. We said the value of n equal 3. That means I'm going to use them. This one unused. Okay, so this one is going to be here, the first one, 0, 0. The second one is going to have another bucket, 0, 1. And the third one is going to be a third bucket, which is going to be 1, 0. Okay. Here, the value of n, I do have 4 buckets I can use. So in this case, I can define this one into 2 parts. I'm gonna call this one the virtual, the real bucket that exists right now. That means, what does it mean exists? That means if you have any hash values, key, that hash to any value, if the value is gonna be start at 0, 0, or 1, 0, or 0, 1, you're gonna find the actual bucket where this value is gonna be stored. Because this value is going to be hashed to the existing bucket is there. If anyone of the hash value of any key is producing our example here 1 1, the first, I'm talking about the hash value with the I bits. Okay, the last I bits is 1 1. In this case, if I search this one, 1 1 does not exist. So how can I find this one? This one is going to point to the bucket that I didn't use yet. Is available but is not used yet, so you cannot use it unless you need it. So in this case, what I'm going to do here, I need to find a way in order to, in this case, since one is going to be mapping to non-existing bucket, or let's say the virtual bucket is not a real one, so I need to do what? I need to do some mapping. So that means try to find a place or any bucket can hold this entry or the hash value until the bucket 1 1 is going to be available. So back to remember the value of n equal 2, then n minus 1 always equal to what? The first bit in the binary representation of n minus 1 always equal to 1. So what does that mean here? If, please pay attention to this one. If I just flip the first bit from 1 to 0. So what's going to happen here in this case? Because any value from start from 1 here is not exist. Any value is greater than n. Less than 2 to the power I minus 1 is not exist. So all the hash value is going to be hashed to non-existent, let's say, bucket. So in this case, I need to do what? As a solution, I need to map this one into one of the existing bucket there. How can you do this one? Flip the first bit that you have from 1 to 0. So if you flip this one from 1 to 0, that means what? This value can be hashing to an existing bucket. 0, 1. Because if you flip this one from 1 to 0, definitely that means the number is going to be less than n minus 1. And this one is going to be exist. Because you are using n bucket. Remember that we have n, the binary representation of n minus 1 must equal to 1. That means any number that's greater than n minus 1 and less than 2 to the power I minus 1 is not going to be exist. But it has this property. If you flip the first bit, that means you're going to have the number or the hash value is going to be point to the index of the bucket that exists. So in this case, the 1 1 is going to be hashed to what? Go this one. Let me have a different color. So that means the 1 1 is going to be 0 1. I go follow this one here. Then I'm going to store this one. It's going to be 1 1 and going to be stored here as the entry. Okay. So someone is going to say, okay, but you said here the value here must match. I agree you must match, but if we don't have a bucket 1 1 here, so in this case it's going to be fine. So if you find any unmatch here, But you still figure out that this bucket, that 1 does not exist, so that means it's fine. So later, when this bucket gonna be available, you need to do what? You need to figure out a way in order to redistribute the key, that hashing to existing bucket. Did I lose you? You follow me? This is the key of the whole thing. We're gonna go over this one again, one at a time. But the most important thing for this example, we know that we do have, looks like the logical bucket, hash bucket, and we have a physical, the actual one. The logical can be divided into, which is like array, list that we have, okay, which is that mapping the hash value to the existing bucket. So here, for the logical hash bucket, that's what we have here, we can divide this one into two parts. The first one is going to be like the real bucket, with the bucket that exists, with depends on the value of n, from 0 up to n-1, with the value of n identify how many buckets actually in use right now. But remember, since we have like extra buckets to the power I available bucket, some of them are going to be virtual. It's going to be there, but it's not used yet. So if you try to map any key, search key, to non-existent bucket, or to the bucket that we call virtual, or ghost, is not available yet. So in this case, you need to find a way in order to map whatever the search key that was supposed to hashing or stored in non-existent bucket to existing bucket. How can you do this one? Remember the property that we talked about? We said if the value of n, given the value of n number of buckets in use, we have like a property. Take a look to the n-1. We're going to find out the binary representation of n-1, the first bit always equal to 1. So if you flip this one to the 0, from 1 to 0, so it's going to be changed, the value, hash value, from greater than or equal n-1 to what? To less than n-1. So less than n-1, this means from 0 up to n-1, this means definitely this one, less than or equal actually. Definitely this means all these values must be exist, must be there, must be point or an index to an existing bucket. So we can map this one, store this value there. Then later, when the entry is going to be available, then things are going to be changed. Is it okay, guys? So let's go back to the slide and go over this one again and see what's going to happen here, what's going on. About here, this is, it looks like we have the bucket array, the one that I showed to you. It's going to have two parts. It's going to be here the real one and the one in the virtual. It's there, but it's not available yet. You can use them, but not yet. Okay, so the hash index, generally speaking, do what? It's going to take the last I bits in the hash function value, or the hash value that you're going to produce. Which the value you're going to use, that's the value of m that we use here in order to tell me where are you going to store this value. Okay? We've said, by the way, keep in your mind that we're going to use what's called overflow. And this makes sense, because based on the condition you're going to have, you're going to say sometimes you're going to have an overflow. Okay? Later, when you add another bucket here with the value of n, increase the n by, when add a bucket, what does that mean? That means the value of n is equal n plus 1. We increment the value of n by 1. Okay? So again, you take a look at the hash index, and we notice that the hash index might be the value of the hash index might be greater than n minus 1. So we need to find a way in order to hash it to one existing value from bucket from 0 up to n minus 1. So again, that's what I've said. Remember, you have 1, 1. We try to hash this one does not exist. Oh, this example here, 1, 1, 1, 1. It's 16. Yeah, that means we try to hash this one. Definitely 16 is going to be here, the last one. This one is not existing yet. It's virtual. So in this case, we need to find a map to what? Mapping to non-existent bucket to the existing bucket. I know I explained this one, but it doesn't hurt to go over this one because this is the main key. Back to the property that we have, given n, that means the binary representation n minus 1 always has the first bit equal to 1 or the suffix bit equal to 1. That means if you flip this one to the 0, definitely it's going to be mapping or going to have the hash index for an existing bucket. So we can utilize that. So again, we can come up with, as summarized here, said, if the value of n binary representation of n minus 1, the first bit equal to 1, that means this is the hash index for what? Non-existing bucket or the virtual bucket. So we cannot hash directly. Okay, how can you do this one? That's what we did here. First, before you do this one, I need to add one extra piece of information here. Okay, I will need to do this one. Yeah, I know I covered this one. How can you map it from non-existing one to existing one? Take the first bit, flip from 1 to 0, it's going to be mapping to existing 1, then hash this value. When, by the way, if the value, for example, is, let's say, 1101. This is going to be non-existent bucket. If you flip this one from 1 to 0, 1, 0, 1, I'm not going to store 1, 0, 1, 0. I just use the value, modified value, to tell me where's the hash index that I need to follow. But I'm going to store the actual value later. So the flipping from 1 to 0, just in order to tell me which index I need to follow. Only. Where's the hash index or bucket that I want to store the data. But when you store the data, I'm going to store the hash value, the actual data here without modification. Okay? You're going to see this one in example. Now, one important example, question here. How can you define, or how can you decide when the time that I need to increase or add the value of n by 1, or add another bucket? Remember I said the average occupancy here? That means, for example, if the average occupancy of the bucket greater than the threshold, then in this case must be increase the value of n by 1. As you mentioned, increase the hash value, that means you just add the index by, or increase the value of n by 1. Okay? Or in other words, what does that mean here? When you say n plus 1, that means I'm going to increase, the number of physical buckets that exists there. So that means I'm going to add one extra bucket to the real and reduce one from the virtual. Okay? How can you compute the average occupancy here? This is the form. This I'm going to follow. Actually, we're going to use this formula. But in order to use this one, we need to figure out a way, how can we compute it? It's easy, by the way. Just you need to make sure that you have the right number, how to implement them. We've given you some parameters and the number of buckets that in use. And you know what the value of n. Start actually with 1, 2, 3, 4, 5, and continue. Okay, it's going to be also increased by 1. Okay, we have the R, which is going to represent, the total number of entries that's stored in the index. For example, we have 5 search keys stored there. That means the value of R equal 5. So how many entries do you have in the whole index? Okay, here gamma. Gamma is fixed parameter. How many, it's like we define as a block size. How many entries can you store in one block or one bucket? I'm talking the one bucket. Remember, generally speaking, we said the bucket can store, for example, 3 tuples or 3 entries in general, or 4 or 5. This is the gamma. Tell you, for example, the gamma here equals 3. I can store maximum 3. Okay? Then I need just to follow this one. I compute the maximum number of search key that can be stored in one block is given. And take a look at the maximum number of search key in the block. In this case, you take the number of user block and multiply by gamma. Okay? Then you need to compute the total number of search key that's stored in the whole index. Here, by the way, I'm just taking the value of the, you're not gonna compute the number of the, include, the overflow. Just need to compute how many buckets do you have. 5, 5. If you have one that has overflow, it's gonna be excluded. Okay? I will give you an example next slide. So you take R, the number of tuples that you have or entries, divide by the number of used value of n, multiply gamma. If this one is going to be greater than whatever the tau is given, as an example, maybe going to give you 75% or 85 or 80%. Actually, in the real application or real practical, the value between, I think, 90 to the 92, I guess, or 94%. This is the good optimization, good value for the tau or threshold that you need to use here. Okay? This has example. So here, what's the total or the average occupancy that we can use here? First, I need to have the formula here. We have R divided by n multiply gamma. So take a look. What's the R here? 1, 2, 3, 4. We have 4 tuples or 4 entries in total. Divide by what's n here? N is going to be here 1, 2. I have only 2. It's not the 3. It's 2. Multiply because number of buckets. This is overflow. If you have another one, is overflow. If you have another one, is overflow. I need just only count the number of buckets that you have in use, the value of n. Okay? Then after that, what's the value of gamma? Assume the gamma is going to require the maximum number of entries can store in one bucket is 2. So in this case, I can multiply by 2. So 4 divided by 4 equal 1. So it's going to be 100% this one. Okay? This is how to compute the average occupancy in this case. Clear? Later we're going to see it depends on the what's called the tau. We're going to see the threshold you can define, you can tell whether we need to have expand or not. Okay? Let's take a look. So this is my condition, by the way. This is very important. Okay? So the question here mainly the same thing that we did the extendable hashing. We need to perform some insertion. In the B plus C we did insertion deletion, but for the hash table we do only operation required from you to do insertion. Extendable, and here you need to know how to perform the insertion in the linear hash table. Definitely the final exam on a question. Okay? To the insert record with the key K, what you need to do first, we need to compute the hash value. This is the first thing we need to perform here. Okay? Compute the hash value, then after that, based on the hash value, let's say the key here, you're going to produce whatever the hash value that you have. Remember the number of bits of I, that's the number of bits that we're going to use in order to tell me what's the hash index value, which M. So M is equal to what here? It's going to be the first I or the last I bits here, from the hash value that we have. Assume it's going to be from A1 up to AI, something like this, okay? So you take a look at these bits here, and the best thing, as you mentioned here, we need to do what here? We're going to use like these as integer represented by, as a decimal, from the binary representation to the decimal, because it's easy to work with this one. Because I'm going to say n, for example, equal 5. So then you need to compute the value of n with 5, with n, whether greater than or not. So in this case, it's better to convert this one from binary representation to the decimal. So you know how to perform that, yeah? You know they have 2 to the power 0, 1, 2, and etc. The first 1, 1, 2, 4, 8, and etc. If the value of m is say 1, 0, 1, 1, so in this case it will be 10, 11. Yeah? If all of them equal to 1, this means it's going to be 15. If all 1, 0, 0, 0, so in this case the value m equal 8. Okay? So all of us are familiar with how can you convert that. Anyway, you compute this one as a decimal number or integer. Then now, based on the value, I want to insert something. You compute the hash value. You compute the value of m, which is going to give you the index. Now you need to check whether your index is available or not. In other words, whether the index or the value of m is going to point to an existing index or the real index or non-existing index or bucket, or let's say a virtual one. If it's going to point to the existing one in the real one, that's fine. Just follow this one and store it there. If there is no space, add overflow. If point to non-existent one, that means in this case in the virtual bucket. So in this case, what I need to do here, I need to modify m, flip the first bit from 1 to 0 in order to find, in order to give me an index of an existing bucket. Then I follow this one and store the value, or the entry is going to be stored in that bucket. You follow me? So it depends on the value of m. If the value of m is less than n, that means in this case what? It's pointed to what is called, the real bucket. Or this can say m is real. When I say real, that means has index to the real bucket or existing bucket. The value from 0 up to n. Okay? Then exist, insert the value into that bucket. If necessary, you're going to see that use overflow if there is no space. We haven't done here. If the value of n is greater than or equal to n, what does that mean? Since we have 0 up to n minus 1, those are the existing bucket or the real bucket because we have n buckets. So if the value of n is going to be point here to n plus 1 and etc. up to the 2 to the power I minus 1, so in this case, this is not exist yet. So I need to do what? Take the value of m, flip the first bit from 1 to 0, then this one going to be mapping to from 0 up to n minus 1, follow the index, then store the data. If necessary, you can use overflow. We haven't done. In both cases, either going to be the value of n less than n or the value of m greater than or equal n. In this case, it's going to be virtual. Here, it's going to be virtual bucket. So what you're going to do in this case, after you insert this one, you need to make sure that the average occupancy or the condition that we have is fine. You didn't violate the condition. So you need every time you perform insertion, adding new things, you need to compute the average occupancy, which is going to be the value of r divided by gamma multiply n. This one must be greater than that tau. If you figure out if this one exceeds or satisfies this condition, so what we're going to do in this case, I need to increase the value of index by 1, or the value or the number of buckets by 1, or the physical buckets by 1. Then, after that means, since we have, for example, assume n equal 3, 0, 1, 2. Now I said n is going to be 4. I add another 1, 3. If we add another 3, that means we have a new bucket 1, 1. What we need to do here, maybe there's some few keys that's supposed to hash into this bucket, But at that time, the new bucket wasn't available, was virtual. So I need to do what? I need to figure out or find these keys and hash into the new bucket. How can you do this one? So the thing, when you add a new bucket here, take the bucket index is 1, 1, flip the first bit from 1 to 0, and go to that bucket here, and that bucket is going to find the candidate. If there is any search key, or the hash value start with 1, 1, this means this value is going to be stored in this bucket. So go to the bucket 0, 1, which follow here, and check whether they have like search key start with the 1, 1. If you found them, move them here. Then again, compute the average occupancy and see whether everything is fine or not. You get that? We need to have an example to understand what's going on here. So let's give you an example here. Assume that the maximum number of search key in the one block is, gamma can be stored in the maximum number of entries. It's going to be 2. The threshold, average occupancy tau is going to be equal 85%. 0.85. Good. I give you this one. This is initial state. Assume that sometimes either you have to start at the beginning. I think next lecture I'm going to give you this example, quick example. How can you do this one when you start this one from the beginning? The initial value. Okay? So here in this case, the initial state, or the given state here in this case, how many value of n is 2? How can you tell? We have 0, 1. Okay, or 2 buckets here. Good. What's the value of I? How many bits you can use? Equal to 1. You need to specify what the value of n, I, and the value of r every time before migration. Okay? What's the value of r? How many tuples you have stored here? 1, 2, 3 tuples. Or entries stored in the index. Good? So let's compute the average occupancy. First, when you start with this one, double check the average occupancy. Maybe before you're doing anything, you need to maybe add or modify the data. So check this one. Average occupancy, as you mentioned, that's what I said is very important. You need to compute the value here. R divided n multiply gamma. R3 divided by n, we have 2. And we have the gamma is 2. So in this case, 75%. This is then 85%. That means there is no need in order to increase the bucket by 1. So now you're all ready to perform any operation. So assume that I want from you to insert 0, 1, 0, 1. Assume you're going to use the search key and the hash value that you're going to use is going to produce 4 bits. Okay? So what I'm going to do here, I will check this one, the hash value here. I'm just interested with the first bit here, which is going to be 1. Yeah, I'm working with like the last I values, which in this case 1. Right? Check this one. 1 is going to be hashing this index. Follow the indexes exist. Then it looks like what's the value of m in this case equal to 1. Is m is what? Is less than equal to n. So you are fine. So that means it's going to be the value of n is exist. So there is no modification you need to perform here. Okay? So if the value of m less than n, okay, then what we're going to do in this case, follow the pointer equal to 1, and you're going to store the value here. It's going to be here in this case, it's going to be 0, 1, 0, 1, and the store. This is the entry, and this is the pointer. Right? I'm done. No, we haven't done. Once you do this one, you need to compute the average occupancy again. So what's the average occupancy here? Equal to 1. You need to compute n divided by, it's going to be r divided by n multiply gamma. What's the value of r? 1, 2, 3, 4 now. We have 4. Okay, what's the value of n? Still we have 2 buckets. The gamma is fixed. It's going to be 2. So it will be here 1. It's like 100%. It's greater than, let's say, 85%. Or let's say 1 is greater than 0.85. So in this case, if we exceed this one, that means we need to react. We need to add another bucket. So can I add another bucket here? Yeah, if you add this one, that means the value of n now is equal to what? To the power I. So if you add another one, you need to increase the value of I that you need to perform. Let's do this one. I'm going to add another bucket. So when you add another bucket, that means in this case, I need to say what? By the way, you need to update the value of r equal to 4 here. So when you add this one, so it's 0, 1, 2. So the value of I is equal to 2 because I need 2 bits in order to represent that. And the value of n is equal to 3. Now we have 3 buckets. If you have 3 buckets here, let me clean that. I'm going to add another bucket too. So just update the data here. 4, 2, this is 3. And this point here, I'm going to do 0, 0, 0, 1, 1 0 in order to help us in order to represent the data more efficient. I add a new bucket. Then after that, what you need to do here, I need to check, since I add 1 0, flip the first bit from 1 to the 0, and check that bucket that has index 0 0. See whether you have any bucket that starts from the 0 1 or not. Because here we have 0 0. The first one 0 0, but this one 0 1 is supposed to be not available, stored here, because the existing bucket is there that have the 0 1 0. So follow that one and redistribute the keys among them. So there'll be 0 1 0 1. This one does not exist anymore here. Then compute the average occupancy again. We have R divided by N multiply gamma, R still 4, N equal 3, multiply gamma 2, which will be 4 divided by 6. This is definitely less than 75%. Okay? So that's what happened here with more details here. It's going to be, I think, 76. Something like this, whatever. Okay? Let's take a look here at the slides here. So at the beginning here, let's do this one again. This is the entry, the initial state. Now I want to insert a new item here. Check the hash value based on the value of I equal to 1. Follow the index. The index tells me this is the place that you're going to store the data. I do have a space, then I'm going to store there. Then after that, you need to compute the average occupancy. I find this one, there is what? Is greater than. So satisfy the condition. In this case, I need to increase the value of N plus 1. Add another bucket. You add another bucket. If you add another bucket, make sure that you update everything here. So add another bucket with the 1 0. Okay? Then in this case, you need to do what? N equal 3. Update by 1. The value of I 2 bits in order to represent this one. Those are many important. You have to give me the parameter every time you modify, every time you insert a new tuple in the relation, or something changed. Then the value of R 4, we have 4. Then now I add a new bucket. If you add a new bucket, take a look to the first bit. Flip this one to the 0 0. Then take a look to the bucket that starts indexed by 0 0. And try to redistribute the key. Remember we said we're going to perform the operation that we got. It looks like we expand the size of the hash function, or the number of buckets that we have. And under the condition here that we are going to do what? We are going to reshuffle or rehashing only fraction of the hash function, or the entries, not all of them. So that's what I'm going to do. It looks like hashing from here to here. Based on the first bit must be 1 0, so it's going to be 1 0 here. The same thing that we did here. We move this one, sorry. Hashing here, and this is what's going to happen here. Now I'm going to do what? I'm going to just compute the average occupancy again and to check and see whether it makes sense or not. Any questions? Is it clear, guys? Let's have an example. How can you search for a specific number at any entry? Assume that the hash value 1111. And again, our assumption that the hash function is going to produce only 4 bits. Okay? So in this case, 1111. Let's check this one. When you search, you need to consider how many bits based on the value of I. It's 2 bits. 1 1. Okay? By the way, change. That means from the original 1 it changed. That's the meaning of change here. Anyway, 1 1. Take a look. 1 1 does not exist. Must be hashing here, but this one is what? Is the virtual. This one does not exist yet. So what we're going to do, flip this one, the first bit from 1 to the 0, definitely going to hash the one existing one. And go to that 0 1 bucket. This helped me in order to figure out or find if the search key that hash value has the hash value 1111 exists in the index, you're going to find it in the bucket 0 1. Go there. That means you need to fetch this block to the main memory. Then after that, perform a search. So you find out this exists. Then after that, you need to follow the pointer that in order to get the rest of the information. Okay? What if we try to set 0001? So 0001, try to set this one in the system. Okay, the first bit 01, because I mean 2 bits, there'll be 01, or the last actually, 2 bits 01. Okay, 01 exists, follow this one. Okay, 01 here. We don't have a space. I didn't care about the order, by the way. Okay, then I'm gonna add another, let's say, overflow block. Then after that, I'm adding this entry here. It'll be 0001, and they have a pointer. Okay, are you done? No. You need to compute the average occupancy. Every time you modify something, you need to compute the average occupancy. Now the value of I equals 5, then you need to compute because 1, 2, 3, 4, and 5 tuples or entry are there. Average occupancy again. You see that the same formula you have to use. The first one is going to be R divided by N multiply gamma. So what's the total number of tuples that you have? You have 5 divided by N, in this case 1, 2, 3. We have only 3 buckets. Multiply gamma, as we said, 2. So we have 5 divided by 6. Definitely this one is going to be what here? So that means you're going to have like overflow. Yeah? Which point? Actually, don't overflow, yeah? No. Because this one is going to be this value. So 0.83 and the threshold that we have is going to be 0.85. So in this case, we are fine. We don't need. So you see that we have overflow blocks. That means we don't need to have extra buckets here in this case. Okay? Good. Again, make sure that you update this value, the current value. Let's try to insert 1111. 1111, you know that. Take a look to the last I bits. In this case, 2 bits. The 11. 11 is going to be pointing to non-existent one. It's not there. So what I'm going to do here, I need to hash this one to existing one. Flip the first one from 1 to 0. And 0, 1, that means follow this index, the new tuple, or sorry, new bucket. And this one, there is no space. That means I need to store this one here. Okay? Which is going to be 1, 1, 1, 1. And this is the point. Before I proceed, what's the cost of inserting, let's say 1, 1, 1, 1 in this case? When is this the cost? How many disk input out operation you need to perform in order to store that? How many disk IO I need to perform in this case in order just to store this element in the right place? What do you think? 3, exactly. Because what we did first, exactly, I need to fetch this one, the block, search, identify. We assume this one is going to be in the main memory. So that one is going to be easy for us. That as the previous assumption. You ask this one, fetch this one to the main memory, this one disk input out operation. I didn't find it. Then I know there's overflow. Ask this one, so another disk input out operation, the second one, or another disk input out operation. We do have space, store the element. Then after that, we need to change or store this one in the disk. So another input out operation. So the total is going to be 3 disk input out operation here. Okay, good. We did this one. We stored this one in the place, but doesn't mean that we have done, because now R6, I2, and N equal 3. Every time modify something, you have to check, the average occupancy, see whether, achieve, whether satisfy the condition that we have or not. So in this case, we have R divided by N multiply gamma. Always we have the same formula. We have 6 here. We have 6 elements. Well, entry 3, 4, 5, 6 divided by N, which you have 1, 2, 3. You see, I'm not going to say N equal 4. I'm just talking about the number of buckets here, which in this case, 3. Multiply 2 is given a fixed number gamma, so it's going to be 1 is greater than 85%. That means definitely we need to add a new bucket. Now, if you add a new bucket here, you know that now the bucket 1, 1 is going to be available, the virtual one. Do we need to add, increase the value of I here? No, we still need, still have, enough that we have I equal 2 bits in order to represent from 0 up to 3, in order to represent, N buckets in this case. So that's perfect here. So when you add another bucket here, so the other bucket is going to be something here. And this one is going to be a point here, and the entry 1, 1. If you have a 1, 1, every time you add a bucket, what you need to do here, we need to redistribute a fraction of the search key that exists there. Because there's a chance, maybe, before this adding the new bucket, before that, maybe there's some set of search keys that hashing to a different bucket. It's supposed to be hashing here. So how can I do this one? We have a 1, 1, check 1, 1, take a look at the 0, 1. Because you see, try to reverse operation. Every time try to have the sort of hash value, hashing, let's say, search key that hash values end up with 1, 1. We flip this one from 1 to the 0, the first bit, in order to hash to that index or that bucket. 0, 1, check 0, 1. Here. This means I'm going to lock this one here. Can you rehash the value here? Take a look at the value that start with of the last I bits is going to be 1, 1. So in this case, this one here and this one. Both of them are going to be moving here. If you're moving this one here, that means this one is going to be moving here. Then you're going to delete or get rid of the overflow block. So that's what happened here. I added one, new bucket. Then after that, you need to perform what's called, and here the value of n equal 4, update this. Then now you need to search or rehash the key from the bucket 0, 1. Someone will say, can you take any bucket? No, this one must be 0, 1, depends on the value here. Yeah, it depends on the value of a new bucket that you want to insert. Then after that, you hash the new values between the bucket 0, 1 and let's say the hash the existing search key that's stored, or the entry stored in the 0, 1, between 0, 1 and 1, 1. And that's what we have. Then after you finish, now you need to compute the average occupancy again. Make sure that you satisfy the condition. Make sure that, there is no need to add a new bucket and continue this operation. Okay? So that's all actually about the hash value here. The linear index. So take a look, to manage growing files more efficiently, there is no interaction like extendable hashing. Yeah? But the problem, compared to the extendable hashing, because just to compute the hash value, then done, the indexing. Can still have overflow chains. This is the most problem. But we acceptable here. Because at most, basically, the research papers or the researchers find out that, at most, we have only one hash, or you say an overflow. Then later, maybe after add another bucket, this overflow is going to be disappeared. So at most, you're going to have one overflow. So let's say in the worst case scenario, the order to look up any entry here is going to cost you 2 disk input out operation. The first one, and at most one another, let's say, overflow block in order to search. After the assumption, this one's going to be available in the memory, and this is easy. Just it has the value just to tell you how can you find the bucket that you're looking for. The problem here, but we don't like, people don't like, the overflow that you have. And also you need to have redirect or bucket when you're creating a new one. You need to redistribute the keys or reshuffle the keys, and sometimes you're going to delete the overflow block. Remember what we did here, what we did here. We move, this key to here to the new bucket, and also we move that key one, because here we have a space in order to get rid of the overflow and move or shrink, or let's say compress the data on one block. That's going to be it's going to affect the overall performance. But compared to the extendable hashing, still this is a good option. Okay? So the conclusion that we talk about here, the fast data structure, generally speaking, with the hash table, that's supposed to be O1 looks up, hopefully, in most cases, if you don't have overflow with the extendable hashing. Okay? We do have trade-off between the speed and flexibility. This is fast, but in this case, you try to add, and also the waste of the space, because you're going to have a number of buckets and multiple data that are going to be hashing the bucket, and also you cannot answer the query directly based on the index. Using the hashing index, if you have index based on the hashing, in this case, you cannot tell based on the index whether the data exists or not. So the hashing just points you, just to direct you to the best location, or the location that you need to follow. If the data exists, then you're going to find it there. Okay? Generally speaking here, we are not going to use the hash table in most cases by default, as I mentioned, or most of the database management system. I'm keeping saying most because I don't know all of them. So in order to be safe, you can't say all of them. By default, when you create an index, it's going to be B+3 index, or B3, they call B3, but actually it's B+3, that the one that we showed you how it works. Okay?